In this lecture, cryogenic liquids and low temperature physics will be covered. Cryogenic liquids are the liquefied gases with a low boiling point at atmospheric pressure. We use LNG or LPG as a fuel in our daily lives. Liquefied natural gas or LNG has a boiling point of minus 162 degrees in centigrade. Methane is the primary ingredient of LNG. After being liquefied, the volume of the LNG gas is decreased to 1 over 600. Liquefied petroleum gas or LPG is produced by lowering gas temperature below minus 30 degrees in centigrade. Propane and butane are the LPG's primary ingredients. After being liquefied, the gas, LPG gas is reduced in volume to 1 over 250. The other gases, such as hydrogen, nitrogen, oxygen, and others, are liquefied for use in a variety of applications, including medical care, academic research, and rocket propulsion. Low temperature physics is a branch of physics that investigates physical phenomena below liquid helium temperature, which is 4.2 Kelvin or roughly minus 269 degrees in centigrade. Nuclear ordering, low temperature superconductivity, and the physics of liquid helium are few examples of low temperature physics. I will now briefly explain the lecture's order. The temperature scales, the development of gas liquefaction, the method of manufacture of cryogenic liquids, and their applications in science and industry will be covered first. After that, we will go over the various techniques for lowering temperature below the liquid helium temperature. We will then investigate the various low temperature thermometers. Finally, we will look at various physical phenomena that are studied using these low temperature techniques. We will also briefly discuss the laser cooling techniques used to reduce neutral gas to temperature below microkelvin. The temperature scales first. Temperature is a numerical value that represents how hot something or somewhere is. There are a number of different temperature scales to choose from. For everyday use, the Celsius and Fahrenheit scales are the most common. The Celsius scale is widely used around the world. In contrast, the Fahrenheit scale is only used in a few nations, including the United States. Kelvin is the designer of the Kelvin scale, which is a thermodynamic temperature scale. This Kelvin scale, commonly known as the absolute temperature scale, is mostly utilized in academia. On the Celsius or Fahrenheit system, the temperature is calibrated in relation to two fixed points, namely the steam and the ice points. The ice and steam points are represented by the numbers 0 and 100 on the Celsius scale, respectively. The interval between the ice and the steam points is then divided into 100 sections. Temperatures above the steam point and below the ice point are divided in the same way. The ice and steam points are 32 and 211 respectively on the Fahrenheit scale. As a result, there are 180 divisions between the ice and the steam points on the Fahrenheit scale. Thus, the following is the relation between the Celsius and the Fahrenheit scales. F equal 905 C plus 32. That is the relation between Celsius and Fahrenheit scales. To determine the temperature, we can use any temperature-dependent physical property. In resistance thermometers, for example, the temperature is determined by the temperature-dependent electric resistance of metals or semiconductors. The standard temperature must be provided by the material independent thermometer. An ideal gas thermometer is employed for this purpose. A gas is defined as an ideal gas when its density is sufficiently low that the interaction between gas molecules can be ignored. Regardless of the kinds of gas molecules, the physical properties of these ideal gases are the same. As a result, for standard temperature definition, a dilute or ideal gas thermometer can be utilized. The ideal gas thermometer is depicted schematically in this figure. A gas tank contains a dilute gas that is connected to a mercury manometer through flexible holes. So this gas tank, this is mercury manometer. The gauge pressure of the gas at constant volume is measured by changing the temperature of the gas tank. So we will measure the pressure of the gas at constant volume. Okay. To maintain the constant volume condition, we raise or lower the mercury tube on right side until the mercury on the left side just meets the position indicated by A in the figure. So at this point, so gas is contained in the same volume. So and we can measure the gauge pressure of the gas. Then that gives us the pressure of gas as constant volume. Okay. So by changing the gas temperature, so we heat up the gas or lowering the temperature of the gas. The ideal gas thermometer measures the gas pressure at constant volume. Okay. By raising this tube, mercury tube, raising or lowering the right mercury tube, this tube, the left mercury column is set at this point, A. So then we can satisfy the constant volume condition. So as we know, the ideal gas duration is given by this equation, PV equal nRT. So P is pressure of the gas and V is volume, and T is the temperature. So N represents the mole of gas and R is gas constant. So T is represented by this equation, and we fix the volume. So these values are constant C. So temperature is linearly dependent on the pressure of the gas. Okay, so if we measure the gas pressure, then we can determine the temperature of the gas. In the figure below, the pressure of an ideal gas is plotted as a function of temperature. Okay. The temperature at which the gas pressure vanishes is determined to be a minus 273.1 degree in centigrade. So this temperature, we extracted the data, then we can get this point. We call this absolute zero. So no pressure of the gas is measured. Absolute zero is the name given to this temperature. This result is independent of the type of gas we utilized. The temperature at which the kinetic energy of gas molecules vanishes is also known as absolute zero. The relationship between a gas's kinetic energy and its temperature is given by the kinetic theory of gases, E equal 2/3 kBT. In ideal gas, there is no potential energy, the interaction between molecules. The gas has only kinetic energy. So this kinetic energy is related to the temperature by this relationship. This is given by the kinetic theory of energy gases. So the gaseous energy, total energy, is directly related to the temperature, and the temperature and the constant. This is constant, so Kb is Boltzmann constant, so it's a known value. So energy of gas is only dependent on the temperature of the gas. So the Boltzmann constant and the temperature are represented by Kb and T respectively. The Kelvin scale uses the pressure of an ideal gas to determine absolute temperature or Kelvin temperature. To completely describe the temperature, we require a standard fixed point that corresponds to a single repeatable state. The triple point of water, the temperature at which ice, liquid water, and water vapor coexist in equilibrium. So that is called triple point of water, was designated as the standard fixed point by international agreement. This triple point is 0.01 degree in centigrade. The triple point of water becomes 273.16 Kelvin if absolute zero, this value, is considered as zero. on the Kelvin scale. The Kelvin scale is represented by K here, Kelvin here. We get the following relationship because the ratio of two temperatures T and triple point temperature is directly proportional to the ratio of corresponding gas pressure P and PT. So T is proportional to the pressure at that temperature, and temperature of triple point is also proportional to the pressure at the triple point. Here, TT and PT are the temperature and the pressure at the triple point respectively. We know the temperature at the triple point 273.16 Kelvin. So any measured gas pressure temperature can be converted as this relationship. Here, PT stands for the pressure of gas at 610 Pascal, or that is pressure at triple point water. So we know the pressure at the triple point 610 Pascal. This one. So once we measure the pressure of gas, then the temperature can be determined by this equation. Okay. The division of temperature on the Kelvin scale is the same as on the Celsius scale, centigrade scale, with the exception that 0 is shifted to this value, minus 273.15 degrees in centigrade in Celsius scale. As a result, the absolute temperature T is related to a specific temperature T on the Celsius scale as follows. So the Celsius temperature T is given by absolute temperature minus 273.15. Now let's see the temperature measurements. Thermometers are used to measure temperature. A thermometer is a device that uses a physical quantity of material that changes with temperature. Any physical property that changes with temperature, such as volume, resistivity, or color, can be used to measure temperature. However, not all physical quantities can be utilized to measure temperature. It cannot be used to measure temperature if the change in any physical quantity with the temperature is too small or too large to detect. The change of any physical quantity should be appropriate to measure with present technology in order to be suitable for temperature measurements. For measuring the temperature of the human body or the air, mercury or alcohol thermometers are commonly used. The volume of most materials increases as the temperature increases. This volume change is used by mercury and alcohol thermometers to determine temperature. A mercury thermometer is a glass tube with a bulb at one end that is sealed. The bulb and a part of a tube contain mercury, while the remainder of the tube is empty. On the Celsius system, the temperature of a mixture of water and ice is defined as 0 degree in centigrade. To calibrate the mercury thermometer, it must first be immersed in a solution of water and ice. The volume of mercury at 0 degree in centigrade is equal to the height of mercury in the tube, thus mark 0 on the outside of the glass tube. The thermometer is then immersed in the boiling water. Boiling water has a temperature of 100 degrees in centigrade. In this boiling point, boiling water, the mercury expands, increasing the height of the mercury in the tube. A second mark is made on the outside of the glass tube to reflect the volume expansion of mercury at 100 degrees in centigrade. On the thermometer, the intermediate temperature marks are made by dividing the distance between 0 and 100 into 100 equal intervals. Above 100 and below 0 degree, the same interval is extended. The volume thermometer can be alternatively be made out of alcohol instead of mercury. Because alcohol is colorless, the red dye is blended with it to provide a clear indication. We normally use the thermocouple in the refrigerator or air conditioner or some other household equipments. And this thermometer is made by two different metals, and this joint at one end and measure the voltage between two metals. And this voltage is changing with temperature, so we can determine the temperatures. So the temperature at this point is changing, the voltage is changing. So if we measure this voltage change, then we can determine the temperature at this point of joint. So metals have different electron energy levels. So this electron energy levels in this metal and in that metal is different. So as a result, when two metals are joined at one end, okay, then the voltage difference can be detected at the other ends here. As the temperature of the joint changes, it also changes this voltage. So voltage is changing as function of the temperature change here. So this voltage change can be used to determine the temperature at the joint here. Thermocouples are frequently employed in heaters, air conditioners, and refrigerators to measure temperatures. A thermocouple is made by joining two metals together. The voltage is then generated between two metals. Because the electron energy levels in two different metals are different, so we can measure the voltage difference between two ends of the thermocouple. Temperature affects this voltage. The thermocouple is useful for controlling the temperature of the electric apparatus, since it produces a voltage output. Right? If a heater is set to a specific temperature, for example, the thermocouple, the temperature is electrically controlled by comparing the thermocouple's output voltage to the corresponding voltage at the set temperature. Okay. So there are several different types of thermometers that have been designed and are now in use. So you can see in this table there are various types of the thermocouples, and the range of the thermocouples are different. For example, let's see Carmel Constantan. The temperature range to measurement is minus 200 to 1000. Okay. During this temperature change, you can measure the voltage change minus 8.8 millivolt to 68 millivolt. Okay, so temperature range are all different, right? So we can choose some couples for our applications. Now let's see the temperature regulation of the human body. The special neurons in the brain's hypothalamus, this region, measure and then regulate human body temperature. Through experiments, this has been proven. In this experiment, the hypothalamus has electrodes inserted to alter its temperature. So if we use electrode connected here, hypothalamus, and we can change the temperature by heater, this heater. Okay. So in this experiment, the hypothalamus has electrodes inserted to alter its temperature. Even if the rest of body's temperature remained constant, they discovered that the body's temperature control mechanisms are fully functioning. The rest of body's temperature remains at 36.5 degrees in centigrade, but we just increase the temperature of our hypothalamus by using the heater. Then this temperature sensor feels that temperature is too high, so temperature heat releasing process is functioning. Okay, so heat loss mechanism such as vasodilation and sweating are triggered when the electrode heating keeps the hypothalamus's temperature above this body temperature. However, when the hypothalamus's temperature is kept below 36.5 degrees in centigrade, then we need heat generating process, right? So heat generating or heat conserving mechanism, including vasoconstriction and shivering, are triggered. So in this experiment, we knew that hypothalamus measures the temperature and regulates the human body temperature. The hypothalamus's set temperature can be rise above 36.5 degrees in centigrade due to the pyrogens generated by the bacteria and deteriorating tissues. Even at 36.5 degrees in centigrade, the body feels cold in this situation. As a result, shivering and vasoconstriction continue until the hypothalamic set temperature falls to 36.5 degrees centigrade. The patient experiences a fever as a result of the heat generating mechanism during this process, but does not feel warm because the set temperature was raised due to this hypogenes. The set temperature was increased by this hypogenes above 36.5 degrees centigrade. So the body doesn't feel warm because the rest set temperature was raised. Okay? The patient feels warmed when the pyrogens are eliminated. Okay? Then the set temperature is returned to their original value of 36.5 degrees centigrade. So the patient feels warmed. And the body's heat loss systems are activated on to low the 36.5 degree body temperature. So in this experiment, we can identify which part of the brain is controlling the temperature, and that was the hypothalamus regions of the brain. So this region